Okay, today we're going to do Chapter 1, Section 2 for Calculus. It's on functions and graphs. Start with a few definitions here. A relation is a set of ordered pairs. So anything that can be written as a set of ordered pairs is called a relation. The set of the first entries of the ordered pairs is called the domain. Typically, we use the x variable for that, but it does not have to be the x variable. The set of the second entries is called the range. That's the output variables. In most cases, that's the y variable. But again, it doesn't have to be. It depends on how we describe that relation. The points in the coordinate plane that correspond to the ordered pairs of relation form the graph of the relation. A relation does not necessarily have to be a function. A function is a special type of relation, and that's what we find out in our second definition. A function is a relation that assigns a single element of R to each element of D. In other words, if you plug in a value for X, you can get one and only one value out for Y. You cannot get two different values of Y for one value of X, or you cannot get two different range values for one domain value. A nice way to test it if you're given the picture is to use the vertical line test for a function. If every vertical line in the xy plane intersects the graph of a relation and at most one point, then the relation is a function of x. So if you think of something like an ellipse or a circle, if you draw a vertical line, you would cut that graph in two places, all except for on the ends. Okay, so if you can cut the graph in more than one place, then that is a relation, but it is not a function. If you think of a parabola, if you draw a vertical line at any point on the graph of a parabola, you will only cut that graph in one place if the parabola opens up and down, up or down. Therefore, it is a function. So many graphs are functions, but not all. Hyperbolas, ellipses, circles are not functions. Those are relations. But many of the things that we will graph this year will be functions. Another thing that we need to do is test for symmetry. In order to test for symmetry for graphs, there are a number of different ways that you can look at it. One way to test symmetry about the y-axis. If x comma y is on the graph, then negative x, y is on the graph. So if you think about it, if something is symmetric about the y-axis, that means it cannot be a function. As soon as let me take that back. Okay, if something's symmetrical about the y-axis, okay, it can be a function. It may or may not be a function, but it can be a function. Think of the parabola y equals x squared. Okay, that can be folded over the y-axis. If something is symmetric about the x-axis, if x comma y is on the graph, then x comma negative y must be on the graph. If you think about that, you cannot have a function. If something is symmetric about the x-axis, it cannot be a function because you can draw a vertical line and cut the graph in more than one spot. Symmetric about the origin. If x, y is on the graph, then negative x, negative y is on the graph. Some good examples of these types of functions, something that is symmetrical about the y-axis would be y equals x squared. That's a nice example, okay? Something that's symmetrical about the x-axis would be x equals y squared. Notice that it is not a function. It is a sideways parabola. And then a good example of something that's symmetrical about the origin, you can go y equals x, or if you want to have an example that's a little bit more involved, y equals x cubed. Moving on to the next definition. A function y equals f of x is said to be an even function if f of negative x equals f of x for every x in the function's domain. And it's said to be an odd function of x if f of negative x equals negative f of x for every x in the function's domain. Again, if we come back and look at the examples that I've provided here, a good example of an even function. Make sure, first of all, it must be a function in order to be an even function. If it's a relation, then we don't describe it using the term even or odd. So a good example of an even function would be f of x equals x squared, or y equals x squared. If you plug negative x in for x, you're going to square it, and it's going to turn back to positive x squared. It's the same. So when you plug negative x in for x, if you get the same thing back out, it's an even function. So f of x equals x to the fourth would be an even function. As a matter of fact, if it's a polynomial function, if every term is even, then it will be an even function. So if we think of a parabola that might be x squared minus 4, this is an even function. Constant terms are always even because we can put an x to the 0 after the constant term if we would like. So in this case, we have two terms and both terms are even. Another even function could be a quartic. X to the fourth plus 2x squared plus 6 will be an even function, 2x squared, because every term is even. But that only works for polynomials. It does not work for rationals and others. Okay? Odd. Similarly, if every term is odd, so some examples, y equals x, y equals x cubed, y equals x cubed minus 3x are all examples of odd terms. If I were to put a constant on any of these odd ones here, they would no longer be odd. We would have to say that they are even. We would have to say that they are neither. So functions can be even, odd, or neither. And we'll look at a wide variety of functions throughout the year. Here's some examples with polynomials, but we'll also look at trigonometric, we'll look at rationals, we'll look at a lot of different functions and try to determine whether those functions are odd or even. If they are, it really helps with our analysis and our mental picture of what that graph is going to look like. So it is important to know whether functions are odd or even. All right, the composition of a function. You've done this since Algebra 1, did a lot in Algebra 2, and even more so in pre-calculus. The main thing that you need to know, composition is f circle g of the function f and g, is how you would say it. And it really means when you see this f circle g, a lot of times I will just say fog because it's shorter. When we see fog of x, it's f of g of x. That means you take x, you plug it into the g function. Whatever the output is, you turn around and plug that back into the f function. The domain of fog consists of those x's for which g of x is in the domain of f. We will look at some examples dealing with this, but the main thing that you need to know when you're finding the domain of a composite function, you must consider the interiormost function. If it has a more restrictive domain, then the domain of your composite function must take on that domain. And again, we will look at some examples where you'll be able to see where we need to restrict the domain. Lastly, this one is very, very important. The absolute value function, y equals the absolute value of x, is defined as a piecewise by the following formula. F of x equals negative x when x is less than 0, and it equals x when x is greater than or equal to 0. Lots of students will look at this and say it doesn't make sense. We can never take the absolute value of something and get a negative. But think about this. We're only taking the negative of x if we're plugging in a negative value for x. And if you negate a negative, it becomes positive. One of the problems is oftentimes when we try to teach a certain concept, we try to make it easy as possible. So in many cases, teachers will say absolute value is easy. If you take the absolute value of a negative number, make it positive. Well, what does make it positive mean? It means we have to negate the negative to make it positive. And that's exactly what this definition is telling us. It's telling us if you have a negative number, if x is less than 0, in order to make that negative become positive, you have to negate whatever that input value is. If the number is already positive or 0, then we just leave it alone. We don't have to change it. The reason why this is important is there is no rule in calculus for dealing with absolute value functions. We must convert all absolute value functions to piecewise form before we can apply any calculus rules to that function. You must be very good at rewriting absolute value functions as piecewise functions by the time we leave Chapter 1. It will be expected throughout the rest of the year. So every time that we graph an absolute value function, I will require you to rewrite that function in piecewise form. It will be the majority of the points awarded on a test will be for if you can rewrite the function in proper piecewise form. So please keep that in mind. Moving on to the next page. Here are the first examples. I will put problems just like this on the test. A wide variety of different functions that I expect you to graph. I'll provide the grid for you so you can graph it right on the test. It'll be very similar to the way that this is set up. Sometimes I will ask for even more information than what is being asked for here. But here we're going to talk about domain and range of each function. You can support it with a graphing utility. That means you can use your graphing calculator. I'm not going to do that on here when I'm doing the notes, but you certainly can do that, and I will talk about it in class. We want to graph the function. We're always going to list the intercepts and any asymptotes that might be, that the function might have. We always want to make sure that we label things correctly, so intercepts should always be given as coordinate points. If you don't, you will lose points on the test, okay? All right, so taking a look at this, y equals 2 plus the square root of x minus 1. Hopefully everyone knows what a square root function looks like. Every year this seems to be problematic for Chapter 1. It's very important that you know that square roots, even roots have endpoints. Even roots have endpoints if it's a linear situation underneath the radical sign. So on a problem like the square root of x minus 1, we do not have an asymptote. We have an endpoint. And so for some, it may be helpful for you to look at the domain first. There's really only a few domain restrictions you need to be concerned about in Chapter 1. First one is that we cannot take the even root of a negative number. Whatever is underneath the radical sign is called the radicand, must be greater than or equal to 0. Another restriction is you cannot have 0 in the denominator. We cannot divide by 0. It's undefined. We also are going to have to worry about other domain restrictions when we look at logarithmic functions. You cannot take the natural log or log of a negative number or 0. So there is other restrictions, but the main two that you need to be concerned with are even roots of negative numbers and 0 in the denominator. So when I'm looking at this particular situation, one of the first things that I'm going to say is x minus 1 has to be greater than or equal to 0, because the radicand of an even root has to be greater than or equal to 0. If we add it to the other side, we get x is greater than or equal to 1. I will expect on the first test that you can write the domain and range in both set builder notation and interval notation. So please make sure that you get both of these down. For the domain of this particular function, we will say x is the element of all real numbers. That's how you read it. This is a curved E here, and it means the element of all real numbers. Okay? So let me say it again in case you missed it. We're going to say x is the element of all real numbers. And then we draw a line, and that line means such that. That's how you would read it. Such that x is greater than or equal to 1. I want you to be used to set builder notation. It's used a lot in abstract algebra and linear algebra because there will be other designations. This double-lined R stands for real numbers, but later on we can use Z for integers. There's a number of different ways that we can write using set builder notation that in the end actually saves you a lot of time and effort. So I want you to be familiar with it. We will cut it down later. It's not required on the AP test. We'll cut it down later and just use inequality notation. But for now, I want set builder. And then I also want to see it in interval notation. Interval notation, x is greater than or equal to 1. If we want the number to be included, we use a bracket. So this is bracket 1, comma, positive infinity. We always have a parentheses on the infinity. Include it. Use a bracket. Non-included, use parentheses. That's how you list something in interval notation. If you need to see me more on that, please do, but you should be familiar with this from pre-calculus. Okay? The range, I always think it's best to do range after you've graphed the picture. So when we're done with the picture, we'll come back and fill in the range. Now, many of you probably right now could get the range. Y is the element of any real number. There will be a restriction on this one. Okay? But let's finish the graph, and then from the picture, we can really get an idea of what the range will be. So the next thing that I'm going to want you to do is plot some points. On all of these graphs, I want to see at least 3 or 4 nice detailed points. And what I mean by nice detailed points, I do not want decimals. I do not want a bunch of decimals or try to avoid radicals. Pick good numbers that give you good outputs. You have to think a little bit. Mr. Hearn always uses the terminology, what is the most interesting value of x? And in this case, the most interesting value of x is whatever makes this argument equal 0, which will be the number 1. If we plug 1 in, 1 minus 1 is 0, square root of 0 is 0, plus 2 is 2, the output value is 2. And then pick good numbers moving to the right. We can't move to the left, but the number 2 works really well, and it's often forgotten. 2 minus 1 is 1, square root of 1 is 1, 2 and 1 is 3. But 3 is not a good number. Now we get the square root of 2 here. 4 is not. 5 is a good number, because 5 minus 1 is 4, and the square root of 4 is 2, and 2 plus 2 is 4 for the output. 6 is not good. 7, 8, 9, 10 would be the next good number, because 10 minus 1 is 9. The square root of 9 is 3. 3 and 2 is 5. 4 points is plenty to get a nice picture of a square root function. Plot these points on the graph. On most tests, the grid will be provided for you just like it is in your notes. To the right 1, up 2. To the right 2, up 3. Oops. To the right 2, up 3. To the right 5, up 4. And to the right 10, up 5. Generally, I give you a 10 by 10 graph. So essentially, I expect you to put any nice point that fits on a 10 by 10 grid. Understand square root functions, even roots of linear radicands have endpoints and start and go out. They are half of a sideways parabola. It has an endpoint. There are no asymptotes. Do not list asymptotes for this situation. Okay? Now that we have the picture, we can come back and fill in our range. If we look at this picture, the smallest y value that we get out is 2. There are no values below 2. So our range restriction is y is greater than or equal to 2. To write that in interval notation is bracket 2, comma, positive infinity, parentheses. Please write domain and range in both forms. Intercepts. If we look at intercepts on this particular situation, you can always find an x-intercept by plugging 0 in for y and attempting to solve. But if we do that, if we plug 0 in for y, we would subtract the 2 to the other side and square both sides. That doesn't work when you end up squaring a negative to get rid of a square root. We can take a look at the picture and see that we do not cross the y-axis. Likewise, we do not cross the x-axis. So in this case, x-intercept is none. The y-intercept is none. Don't be surprised if that happens on some of your homework problems and homeworks on tests and quizzes. Here's a nice detailed graph. We've given all of the different domain, range, all the different items that this particular question is asking for. Okay? We're going to use the same directions. We're going to move on now to, we're going to look at a bunch of different graphs here, okay, that we should be able to graph. And that's essentially what we're going to be doing on a lot of these problems. Okay, so here we go. Let's take a look at a rational function then. We looked at a radical. Now let's talk about a rational. A rational means it's written in the form of a fraction. There's a variable in the denominator. There's a variable in the denominator. We have some issues we need to be concerned about. Again, I think it can be helpful to think about the domain right away. The domain in this particular situation, we do not have an even root. We don't have to worry about the even root of a negative number. But what we do have is we have a denominator, and we have to be concerned about 0 in the denominator. If we set x minus 2 equal to 0 and add it to the other side, we get x equals 2. If you want, you can say right away, we know the denominator cannot equal 0, therefore x cannot be 2. That is the domain. Every other real number works, but 2 will not work. So when we list the domain, we're going to say the domain. X is the element of all real numbers such that x cannot be equal to 2. To list this in set builder notation, it will look like this. We go from negative infinity to 2, parentheses, because we do not want to include 2. In union with, and sometimes books will just use a comma here, but it's nice to say in union with 2 comma to positive infinity. That's the domain. Again, we will consider the range after we draw a nice picture. It's important that you know that rational functions can have asymptotes if the denominator equals 0, and that factor that creates the 0 does not cancel with a similar factor in the numerator. If that happens, we can get holes, or what is called removable discontinuities. But if we have factors in the denominator that cannot be canceled out, and they create a 0 in the denominator, whatever number creates that 0 is an asymptote. It has to be removed from the domain. So it's the same number that is removed from the domain. So in this particular case, we have a vertical asymptote. And you need to tell me that it's vertical. We have a vertical asymptote at x equals 2. Once you locate an asymptote, it is nice to go and dot that in right away. In this case, we also have a horizontal asymptote. When we find horizontal asymptotes, there's really a 3-step rule that we're going to need to apply. It will be emphasized again in Chapter 2 when we talk about limits, because when you're finding asymptotes, you're really using limits to discover those asymptotes. So if you've struggled with asymptotes in the past, hopefully in Chapter 2 you can pull it all together. But to get a horizontal asymptote, there are 3 rules, and in this case we have the easiest of the 3 rules. Anytime that the degree on top is less than the degree on the bottom, y equals 0 will be your horizontal asymptote. In this case, we have a constant on top. A constant is always degree 0. On the bottom, we have a line. A line has an exponent of 1. So it's a degree 1 polynomial. The degree on top is 0. The degree on the bottom is 1. Therefore, the degree on top is less than the degree on the bottom. The horizontal asymptote is y equals 0 every time. So we'll dot that in. As I'm dotting it, remember the other rules say this. If the degree on top is the same as the degree on the bottom, then we have to look at the coefficients of the highest degree terms. Whatever that ratio is, that will be your horizontal asymptote. And if the degree on top is larger than the degree on the bottom, then we have some other type of end model behavior. If the degree is 1 larger than the bottom, then we will have a slant asymptote because we will have linear end model behavior. If it's 2 higher, we'll have parabolic end model behavior. In pre-calculus, you only saw slant asymptotes. In calculus, we may have parabolic end model behavior or cubic end model behavior. There's a number of different types of end model behavior. On the test, I'm only going to put a slant asymptote on the test for the Chapter 1 test, at least. Okay? So we are really ready to plot some points now. We just have to be creative about what points we plot. And you have to give some form of a fractional output here to show how you're approaching the asymptotes. So, in this particular case, pick some numbers to the right of 2. A good number to pick to start with would be 3. 3 minus 2 is 1, and 1 over 1 is 1. So we can plot that point right here. And really, if you know how a rational function works, that's about the only point you would have to plot. But I want to see some fractional outputs and show me what's happening as you're approaching these asymptotes here. So essentially, if I pick 4, 4 minus 2 is 2. 1 over 2 is 1/2. If I pick 5, I'm going to get 1/3. And I can see pretty quickly that I just get closer and closer and closer to this horizontal asymptote. Make sure you do not cross the asymptote. Likewise, we could pick a number like 2.5. If we pick 2.5, 2.5 minus 2 is 1/2. 1 over 1/2 is 2. So we can see as we get closer to the vertical asymptote, the numbers just get larger and larger. Check another number if you'd like. Plug in 2 and 1/3. 2 and 1/3 minus 2 is 1/3. If you flip 1/3, you get 3. So as you're getting closer to 2 from the right, the outputs are getting larger and larger. Please keep that in mind when we get to chapter 2. That's how we're going to be able to define what a vertical asymptote is using limits. Let's pick on the other side. If we pick a number like 1, 1 minus 2 is -1. 1 over -1 is -1. There it is. If you pick 0, you get -1/2. And again, we can quickly see that as x gets large in the negative direction, the y values are just going to get closer and closer and closer to 0. It's going to approach a value of 0. We can also pick a number like 1.5. If we pick 1.5 minus 2, we get -1/2. Flip is -2. So the closer we get to the vertical asymptote from the left, the larger these values get in the negative direction. There it is. In this particular situation, when we're looking at the range, range is going to describe the y values. As a matter of fact, it's the only thing we really it's the only time we describe something graphically using the y values. Anything else, we always use the x values, whether it's, when it's increasing or decreasing, concave up, concave down. We always describe that over the x intervals. But the range we describe using the y values. And that's why we say y is the element of all real numbers, such that, in this case, y cannot be 0 because of the horizontal asymptote. It is possible, by the way, to cross horizontal asymptotes. In this case, we do not. But there are times where we do cross horizontal asymptotes. So don't automatically assume that you cannot hit a horizontal asymptote. If we wanted to use interval notation, it would be -infinity to 0 in union with 0 to +infinity. Looking at the picture, we can see that we do not have an x-intercept. It does not cross the x-axis. So the x-intercept is none. We do, however, have a y-intercept. And you can always find the y-intercept by plugging 0 in for x. We already found that point over here. If you plug 0 in for x, it's right here. But you can plug it in and see that it's -1/2. It's a point that we have graphed. Okay? That's everything that this particular function asks for. This function, by the way, is neither even nor odd. When we get to that, you can see that there is no symmetry here. Some people would say, well, it is symmetrical about the asymptotes. That's correct. There is some symmetry in terms of the asymptotes, but it is not symmetric with respect to the x-axis or the origin or the y-axis. So it's not even or odd. It has no symmetry in terms of axis or origin. Okay? Let's move on to another function. A cube root. I picked a cube root just so that you could see a different type of radical. You are going to have all kinds of different functions that you're going to graph in this particular chapter. I'm trying to give you a few, a sampling, so that you can see how to do the domain and range. But the bottom line is you spent months graphing rational functions in pre-calculus, and we have one section in which you're going to be expected to be able to graph all of them. I cannot show you an example of every single one, but if you follow through with the domain, with the range, you point plot using some nice points to get a nice picture of it. You can even sneak a peek at it with your graphing calculator. You should be able to get a good detailed graph, and we will work through many of these in class so that you can see how these are done. But I expect to not have many questions on the examples that I'm going over right here. Go back, look at this online, take a look at these, so we can spend time in class going over more advanced type functions. In this particular case, one thing that you need to know when you're looking at the domain of an odd root is all real numbers. We can take the odd root of negative numbers. The cube root of -8 is -2. We can take odd roots of negative numbers. We cannot take even roots of negative numbers. That's the only problem. So how do we write that? In interval notation, parentheses, -infinity to +infinity. Done. And the nice part about set builder notation is instead of having to write out domain all real numbers, we can use this shortcut version. X is the element of all real numbers. Many problems in the book, the domain will simply be all real numbers. Don't think that you always have to have a domain restriction. We'll see what the range is after we graph a picture of this. Again, pick good values. Don't give cube root answers or decimal outputs. Okay? In other words, the most interesting value of x here is 2 because that makes the argument 0. And 2 minus 2 is 0. The cube root of 0 is 0, and 1 plus 0 is 1. The next most interesting point here could be 3 or 1, either one that you want to decide. We can take the cube root of 1, the square root, or any root of 1, so make sure that you're always thinking about what makes a 1 underneath this radical sign. So if I pick 1, 2 minus 1 is 1. The cube root of 1 is 1. 1 plus 1 is 2. And then I want to keep going. 0 is not a good number. I don't want the cube root of 2. 3 is not. I'm sorry, -1. -2 is not. -3, -4, -5, all bad. -6 is the next best number in this direction. 2 minus -6 becomes 2 plus 6, which is 8. And the cube root of 8 is 2. And 2 and 1 is 3. These are the types of points that I expect you to list on your test. You need to be good at mental math, picking good numbers to get good outputs, not just for graphing, but for all kinds of things that we will do when it comes to the AP test time. To check to see if something is positive or negative, pick good numbers that work out well. Let's go in the other direction now, because we can pick any real number. So instead of 2, how about we pick 3? Because 2 minus 3 is -1. The cube root of -1 is -1. -1 plus 1 is 0. But 4 is not a good number. 5 isn't. 6, 7, 8, 9, none of those are good. The next best is 10. Because 2 minus 10 is -8. And the cube root of -8 is -2. And 1 plus -2 is -1. We have 5 quality points to graph this cubic function. It couldn't be any better. 2 to the right, 1 up. To the right, 1. Let's do that one again. 2 to the right, up 1. To the right, 1, up 2. To the right, 3, up or down 0. We can go back 6, 1, 2, 3, 4, 5, 6, up 3. We can go out to 10, down 1. And let's sketch this nice cubic function. Okay, so there is a nice cubic function. We can see, although this will go down gradually, it will continue to sink forever. And it goes up gradually, it does continue to go up forever. There is no range restriction. We don't have any asymptote to worry about. There is no maximum or minimum point that we have to be concerned with. The range is also all real numbers. So y is the element of all real numbers. In interval notation, negative infinity to positive infinity. There are no asymptotes here. Cubic function, in this case, does not have any asymptote. Most of your asymptotes are going to occur with rational functions and logarithmic functions. When we get to that, we'll be coming up in another section in chapter 1. So, x-intercepts, y-intercepts, we have them both. If we want to find the x-intercept here, let's start with a y-intercept. It's easier. If we want to find the y-intercept, plug 0 in for x. If you plug 0 in for x, you're going to get 1 plus the cube root of 2 back out. And you can just leave it like that when I ask for a y-intercept. You can check it in your calculator to see what that decimal value is and see if it makes sense. But for tests, you can leave it simply 1 plus the cube root of 2. X-intercept, plug 0 in for y. We see we have it right here. If you've already found the point, don't duplicate work, just list it. But if you plug 0 in for y, you can actually solve it analytically. Subtract 1, take the cube root of both sides. Negative 1 cubed is still negative 1. Add the x to the left side, add the 1 to the other side, and we see that x equals 3. But you don't have to show that work. If you got the point already listed, just list the x-intercept. Okay? Should be good in terms of what was asked for in this problem. Later on, we'll have to do increasing, decreasing, potentially concavity. There's a lot of things that we can talk about for functions. 8. Slide 8. Okay, here's another rational function. I tried to give you one more rational function to give you an idea of some of the stuff that is going on in these functions. Okay? Again, I think it's a good idea for you to think about the domain right away. We do have a denominator, and the denominator cannot equal 0. So in this particular case, I think it's good to say x squared cannot equal 0. That means if you take the square root of both sides, x cannot be 0. If x is 0, we get a 0 in the denominator. So here's how we list it. X is the element of all real numbers such that x cannot be 0. Which means negative infinity to 0 in union with 0 to positive infinity. We'll deal with the range after we graph a picture of it. The range here gets pretty interesting. When we look at this particular situation, we can't plug 0 in for x, so let's think about some other numbers. If we plug 1 in, 1 squared is 1, 1 over 1 is 1, 2 minus 1 is 1. Okay? And we can pick some other numbers as well. Let me backtrack here a little bit. That's a good point that we can plot. But let's think about asymptotes. It's a rational function. If the denominator, you have something that makes the denominator equal 0, and that doesn't cancel with something in the numerator, we have a vertical asymptote. So in this case, if you can list the vertical asymptote right away, it's going to be helpful. X equals 0 is the vertical asymptote. Every year I talk to the students about knowing the difference between the two different types of vertical asymptotes. So I'm going to explain it to you right now. Hopefully people can get this down. There are two types of vertical asymptotes. I didn't come up with this terminology. It's a different book. They don't talk about it in our book. But if you can tell the difference between a pole and a volcano, it can make a big difference. If The vertical asymptote comes from a even factor. In other words, we have x squared right here. If the factor that it comes from is raised to an even power, this turns out to be a volcano, is what we're going to call it, even if it's upside down. If you want to call the upside down one a funnel, that's fine. I'm going to call it an upside down volcano. Call it a volcano so that we're using similar language. The reason why this is important is because it will just jump over the asymptote. You'll see as we plot some points here. In the other one that we did, the asymptote was a pole because it was just raised to the first power. If this was x cubed, we would have a pole. If this was x to the fourth, we'd have a volcano. If it comes from a factor raised to an even power, you have a volcano. The interesting part about this particular problem, and maybe we'll wait, but we do have a horizontal asymptote. And many people will look at this and think that the horizontal asymptote is simply y equals 0, because they look at only the rational part and say, well, the degree on top is less than the degree on the bottom. But you can't just look at the fractional part. You got to make it all one fraction. Let's take a look when we plot some points, and we'll get an idea of what's happening here. If we plug 2 in for x, we're going to get 1/4, and 2 minus 1/4 would be 1 3/4. So we have the point 1, 1, which is right here. I'll graph it in a different color so we can see it better. 1, 1 is right here. And then we have the point to the right 2 up 1 3/4. Let's pick one more point just to see what's happening. If we plug 3 in, we get 1/9 for the fraction, and 2 minus a ninth is 1 8/9. It just gets closer and closer and closer to y equals 2. That's what happens. So it looks like this horizontal asymptote is going to be y equals 2. Let's keep doing some investigation. If we plug 1/2 in for x, watch what happens here. If you plug 1/2 in, 1/2 squared is 1/4. Flip is -4. 2 minus -4 is -2. So as you get closer to this vertical asymptote of 1 from the left, our values get larger and larger and larger in the negative direction. They just take off down this direction. There it is. Let's check the other side of this vertical asymptote. If we plug in, we cannot plug in 0, so we'll plug in -1. Look what happens. When we plug in -1, we get 1 back out. Matter of fact, if we plug in -2, we still get out 1 3/4. If we plug in -3, we still get out 1 8/9. So it's the same points on this side that we get. And it still looks like this. Don't cross the asymptote. You got to be very careful. It's kind of hard here because my graph's not very big. Okay, but we want to make sure that we do not cross the asymptote when we graph this picture. Okay? And I know it's coming more over here. Okay? There it is. That's this rational function. Notice, this is really an upside-down volcano, but we're going to call it a volcano because we jump across this asymptote. We jump from there to there. Okay? When it's a jump like that, we call it a volcano. If you flipped it the other way, it would look more like a volcano. Okay? The key here is that we do have a horizontal asymptote. And the horizontal asymptote in this case is going to be y equals 2. If we apply the rule I talked about earlier, how does that work? Well, the key is this has to be one fraction. If we get a common denominator and multiply the 2 by x squared over x squared, we get y equals 2x squared minus 1 over x squared. Now we can apply that rule we learned in pre-calculus that says if the degree on top is the same as the degree on the bottom, then the asymptote will be the coefficient of the highest degree terms, the ratio of the highest degree terms. So 2 over 1 is y equals 2. There's our horizontal asymptote. If we have a horizontal asymptote, then that means that we're going to have a range restriction. In this case, it's only below that horizontal asymptote. It's not above and below. So y is the element of the all real numbers such that y is less than 2. written in interval notation. Now we go from negative infinity to 2 parentheses. Notice, always parentheses with infinity. We have a parentheses on 2 because it's non-inclusive. Always make sure negative infinity is on the far left if you're using interval notation. Okay? X and Y intercepts here. We clearly do not have a Y-intercept, but we have 2 X-intercepts. The X-intercepts are going to occur when Y equals 0. So if we want to find the X-intercepts, come put it right here. We're going to plug 0 in for Y. I'm going to add the 1 over X squared to the other side. Multiply the 2 up. 1 equals 2x squared. Divide both sides by 2. And I'm going to take the square root. When I take the square root, I have to do plus or minus. X equals plus or minus. The square root of 1 over the square root of 2 when we rationalize that is going to be square root of 2 over 2 when we rationalize. Should be able to rationalize in our heads by now. So the X-intercept, Y-intercept is none. The X-intercept is the point. 2 points. You can list them both at the same time. Plus or minus square root of 2 over 2, comma, 0. And we can see from our picture that makes sense. Hopefully you're getting a feel for some of these graphs. Let's wrap up with a kind of a last example or two here. I guess a few more. Here's this one. Determine whether each function is even or odd or neither. Try to answer without writing anything except the answer. Here's how this is going to work. If it's polynomial, the nice part is if it's polynomial, if all of the terms are even or all of the terms are odd, then it'll be an odd or even function. In this case, y equals x cubed. X cubed is odd. It's the only term. Therefore, this is an odd function. Okay? Think about the fact, if we plug in, a good way to check is to just think about numbers. If you plug 1 in, you get -1, you get 1 out. If you plug -1 in, you get -1 out. If you plug 2 in, you get 8 out. If you plug -2 in, you get -8 out. If opposite signs produce opposite results, it's an odd function. All of the O's go together. Opposite signs produce opposite results. It's an odd function. It's symmetric about the origin. It couldn't be any easier in terms of trying to remember how to connect. They all start with O. If we look at something like B, this can be tricky for students sometimes. This happens to be neither. The reason x is an odd term because it's raised to the first power. 2 is an even term because it's constant. Odd term, even term. If it's polynomial and we have an inconsistency, it's automatically neither. I still think the easiest way is to just plug in numbers. If we plug in 1, we get out 3. If we plug in -1, we get out 1. Opposite inputs do not produce opposite outputs. They do not produce same outputs. So it's neither. If we look at C, this is an even function because it's polynomial and both terms are even. All constant terms are considered to be even terms. We must remember that. This is even. Again, think about numbers. If you plug in 1, you get out -2. If you plug in -1, you get out -2. If opposite signs produce same results, it's an even function, symmetric about the y-axis. Look at this one. Here you might say automatically even because we have this x squared term here. And if you look at it, it does turn out to be even because if you plug in 2, you'll get out 1/3. If you plug in -2, you'll get out 1/3. Notice I stayed away from 1 because those are asymptotes. If I plug in 4, I get out 1/16. If I plug in -4, I get out 1/16. Opposite signs produce same results. This is an even function. Many students will look at e, however, and then say, oh, this must be neither because we have some odd terms, we have some even terms. That only works if it's a polynomial, if you're trying to determine whether a polynomial is odd or even. Let's think about what's happening if we plug in numbers here. If we plug in 2, we get out 2/3. If we plug in -2, and I'll write it down for you this time so you can see it. If you plug in 2, you're going to get out 2/3. And if you plug in -2, you're going to get out -2/3. Opposite signs produce opposite results. If opposite signs produce opposite results, it's odd. All of the odds go together, and it's symmetric about the origin. So it happens to be odd. Even though we have some odd terms and some even terms, it's not polynomial. It's rational. That only works if we're checking polynomials. Best way to check, use your graphing calculator to help you as you're doing your homework problems, but think about it numerically. What happens if we plug in opposite signs? Do we get any type of relationship? Test each equation to find what symmetries it has, then draw a complete graph. I probably shouldn't have had you draw a complete graph. They give you the pictures in the book, but I think this isn't bad for us to think about what's going on when we look at something like this. First of all, if we plug in -x in for x, we get the exact same thing back out. And if you plug -x in for x and get the same thing back out, it's symmetric about the y-axis. So it has y-axis symmetry. If you plug in -y for y, and you get the same thing back out, which will happen here because it's being raised to an even power, then it's also symmetric about the x-axis. And you should know if it's symmetric about the x-axis, it cannot be a function. This has to be a relation. It's a relation, but it does not pass the vertical line test. Anytime something is symmetric about the x-axis, it is not a function. So we do not want to describe this as odd or even because it's not a function. We only describe functions as odd or even. If something is symmetric about the x and the y-axis, it is also symmetric about the origin. So this has all three types of symmetry. That is possible. Many graphs have all three types. Because if you plug -x in and -y in and get the same thing back out, it's symmetric about the origin as well. If we were to graph a picture of this, we're going to get y squared equals 1 over x squared when we divide both sides by x squared. And if we take the square root of both sides, we get plus or minus 1 over x, which means we have two different functions we need to consider. Y equals 1 over x and y equals -1 over x. In both cases, we have a horizontal asymptote at x equals 0 or y equals 0 because the degree on top is less than the degree on the bottom. Let me write it again for you. Horizontal asymptote at y equals 0, and we have a vertical asymptote at x equals 0. Let's dot those asymptotes in so we know what we're dealing with. If we graph the first half, just y equals 1 over x. If you plug 1 in, you get 1 out. If you plug 2 in, you get a half out. 3 in, you get a third out. Here it is. If you plug a half in, you get 2 out. There it is. It takes off. If you plug in -1, you get -1 out. -2, -a half. Here it is. Gets closer and closer. If you plug -1/2 in, you get -2 out. There it is. Y equals 1 over x. We should know what that looks like. It should be familiar enough by now. We know what it looks like. But how do we have all four types of symmetry then? We have all four types of symmetry because now if we graph this function, and I'll do it in a different color, but understand both the green and the red represent this relation. Both of them, all of this is being graphed at one time. So if you plug in 1, you get -1 out. 2, -1/2. So here it is approaching the asymptote here. Here's this. If you plug -1 in, you get +1 out. And here it is. That's what it's going to look like. It does not pass the vertical line test, therefore it's not a function. It does not pass, or it doesn't pass the horizontal line test either. But we could fold this graph over the x-axis and get the same picture. That's why it has x-axis symmetry. We could fold this graph over the y-axis and get the same, and they would overlap. The pictures would overlap. That's why we have y-axis symmetry. But we could also fold this around the origin, and the graphs would overlap as well. That's why we have symmetry about the origin, all three types of symmetry. Let's take a look at this one. Very similar. Okay. Hopefully people recognize this as an ellipse. If not, you need to refresh your memory a little bit about circles, ellipses, hyperbolas that were at the end of the book in pre-calculus. To get this in standard form, most of the conic sections that you're going to see in calculus will be nice standard form. You're not going to have to complete the square and have a center that's offset and figure out the foci and all that stuff. It's pretty straightforward. In this particular situation, if we think about symmetry, if you plug -x in for x, you get the same thing back out because it's raised to an even power. So it's going to have y-axis symmetry. If you plug in -y for y, you get the same thing back out because it's being squared. So we have x-axis symmetry. If you plug -x and -y in, you get the same thing back out. So again, we have all three types of symmetry. This is not going to happen in every problem that you see in the homework, but it happens enough. You need to be aware of it. In order to graph an ellipse, the key is we have to have a 1 on the right-hand side. So the first thing we're going to do to write this thing in standard form, in this case, we don't have to complete the square or anything, is divide every term by 36. X squared over 36 plus, this cancels to give a 9. Y squared over 9 equals 1. This is the standard form. We have a center at 0, 0. If you take the square root of the largest denominator, 36 is larger than 9. It's underneath the x. The square root of 36 is 6. So starting with the center, in order to find the vertices, we're going to add 6 to the x-coordinate in the center and subtract 6 from the x-coordinate in the center. So our vertices will be 6, 0 and -6, 0. If you take the smaller denominator, which is 9, the square root of 9 is 3. It's underneath the y. These are called the covertices. It's determined by the larger and the smaller denominators. Covertices will be 3 units away. So we're going to add 3 units to the y-coordinate and subtract 3 units. Those are the covertices. So really, if you just plot your vertices and your covertices, this will be to the right 6, 1, 2, 3, 4, 5, 6. Back 1, 2, 3, 4, 5, 6. If we go up 3, down 3, we will have a picture of our ellipse. Notice that the ellipse is symmetric about the y-axis, the x-axis, and the origin. If it doesn't look like the origin, when something is symmetric about the origin, you not only flip it, but it turns and twists as well when you're looking at symmetry about the origin. Also, remember, the major axis here, it's not going to ask you to find it, but the major axis is the longer axis. In this case, is 12 units long. The minor axis is the shorter axis. In this case, is 6 units long. It could ask you to find the foci, okay, and some other points. But this will be sufficient for you to graph it and for you to determine the symmetry. You don't have to give all the detail in the homework, but it's a good opportunity for me to review how you graph ellipses, because you will definitely see them throughout the year. Here's an early example that you can follow on how to graph an ellipse. There's lesson number 2. What the page number should be right this time. 1.2a, page 17, problems 1 through 4, 6 through 28 evens. When they ask you to graph, I expect good quality points. List all asymptotes and intercepts anytime that they exist in a problem. Write the domain and range out. Be as detailed as possible with your graphs. It will be a heavy emphasis on this first test that you're able to graph all of this material. Okay, please refer back to this after we go over the notes in class so that you can come back and see if there's any questions that you might have. Hopefully, I hit it a little bit when we were done as we went through this. Okay, see you in class.